Hello, welcome to Maths with EJD. We continue with applications of eigenvalues and eigenvectors in different fields. And today, in this particular video, the focus is on quantum mechanics. Okay, so in quantum mechanics, in quantum mechanics, eigenvalues and eigenvectors play a crucial role in describing the measurable properties of a quantum system. Okay, the eigenvalues represent the possible measurement outcomes, the possible measurement outcomes of an observable quantity. While the eigenvectors represent the quantum states corresponding to these outcomes. In a sense, we can see eigenvalues as magnitude, while we see eigenvectors as direction. So that's one way to see the two of them in almost any context in which we look at them. So our objective here in looking at eigenvalues and eigenvectors in quantum mechanics is to learn how eigenvalues and eigenvectors are used in quantum mechanics to determine possible quantum states and measurement outcomes. So let's look at an example. So we're looking at a particle in a one-dimensional box. So consider a simple quantum system where a particle is confined. The particle is confined in a one-dimensional box. The system is governed by the Hamiltonian operator, the Hamiltonian operator, H cap, which represents the total energy. So that means we have H cap phi of x equals E phi of x. Okay, so I mean you can see how it looks already. It looks almost like what we've been seeing for eigenvalues and eigenvectors, right? A lot of resemblance. So here, where E is the energy eigenvalue, the energy eigenvalue, that is the possible energy measurement, the possible energy measurement. Then we have phi of x, which is the wave function. The wave function, that's a quantum associated, the quantum associated with E. So for a particle in a one-dimensional box of length L, the Hamiltonian is given by h cap equals minus small h bar squared all over 2m d squared dx squared, like this. So next, to find the energy eigenvalues, the E's now, to find the energy eigenvalues and eigenfunctions, we solve the Schrödinger equation, the Schrödinger equation, which is minus h bar over 2m d squared phi of x all over dx squared, and that is equal to e phi of x. So that's all we solve, right? And then that leads us to talk about the energy eigenvalue. So energy eigenvalues, the E's now, the energy eigenvalues. So solving this differential equation, the differential equation up there, solving this differential equation, gives the energy eigenvalues. That is, this is what we are solving, right? So it gives the energy eigenvalues as follows. So we have En equals n squared pi squared h bar squared divided by 2m L squared, where the n's are 1, 2, 3, and so on and so forth. Okay, so those are the energy eigenvalues. So where n is the quantum number, n is the quantum number determining discrete energy levels. All right, so can we look at the numerical side of this? Let's talk about numerical example. So let's consider an electron whose weight is m, or rather the mass, right, is equal to 9.11 times 10 raised power minus 31 kg. Okay. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised to power minus 31 kg. 9.11 times 10 raised Okay. In a box of length L equals 1 nanometer, that's 10 raised power minus 9. That's a nanometer. Okay, let me just write that. That's 1 times 10 raised power minus 9 meter, like that. Then we have that. So Planck's reduced, using Planck's reduced constant, which is h bar equals 1.055 times 10 raised power minus 34 joule second. So we compute the first three energy levels as follows. So the first energy level, E1, of course, En is what we have here, right? So n squared pi squared h cap squared all over 2 ml squared. So the first energy level, that means n is equal to 1. So we have, instead of n squared, we have 1 squared, then pi squared. Then what else do we have there? We have the h cap squared, and h cap is, h bar squared rather. So that is 1.055 and all that. So that's 1.055 times 10 raised per minus 34, all squared, all of that, all over 2m. M is the mass. That's 9.11 times 10 raised per 31. So that's 9.11 times 10 raised per minus 31 times L squared. L is 1.10 raised per minus 9 meter. So that is okay, that's 1 times 10 raised per minus 9 actually. So that's 1 times 10 raised per minus 9 all squared. So if we compute this, E1 is equal to, is approximately 6.02. It's 6.0292 times 10 raised per minus 20. 10 raised per minus 20. Okay. And, we can convert it into electron volts, which is a common practice. And that means that will take it to approximately 0.3768 EV, 0.3768 EV. I think the division is by I think 10 raised per minus 6 or so. Yeah, I'm going to show the Python code, so all of that will be clear there. Okay, so that's the first energy level, right? So the next is the second energy level, that's E2. Interestingly, from what we have here, right, the first energy level is 1 times whatever. So the only thing that will just keep changing is the n. So you can see that from here now. So if you look at this, this is like the first energy level, E1, would actually just be pi squared h bar squared all over 2 ml squared. So the second energy level will be n9 is 2. So that's 2 squared, which is 4. So it will just be 4 of all of this. So we have 4E1. Then the third energy level will be n is 3. So we have 9E1, basically. So with this, we don't have to keep going through the motions. We can just multiply the first one like that. So E2 now will just be the second energy level will just be approximately, it will be approximately zero. So E2 is equal to 2 squared E1 in short. That means we have 4E1, and that is 4 times 0.3768 EV. So E2 is simply approximately 1.5072 EV. That is the second energy level. Okay, then we can go for E3 also. So again, E3 will be 3 squared multiplied by E1. So we have 9 E1. That means we have 9 times E1 again is 0.3768 EV. And then that we have that is 3.39 12 3.3912 eV. That's our the third energy level. Okay. So with that now, so those are the energy levels in short. Well, I mean, I may just take the pain to say, thus the energy levels for an electron in a 1 nanometer box are approximately. So E1 equals 0.37, 0.38, right? That's 0.38 eV. Then E2 is 1.51 eV. Then E3 is 3.39 eV. But that's not all. We have to still talk about the the eigenfunctions. So what we've talked about here so far are the eigen. Oh, so far we've been talking about the eigen energy levels, right? So let's talk about the eigenfunctions. Eigenfunctions, which are of course still the wave functions. Wave functions. So here, the corresponding eigenfunctions, eigenfunctions or wave functions are, so phi n x, that's the general expression, which is square root of 2 over L sine n pi x all over L, like this. So this is the general formula for that. And from there, we can get the results as follows. So for the length of 1 nanometer, the first three eigenfunctions are phi 1 of x, that is root 2. That would just be, of course, we have all the L, the nanometer, and all that. So, so that would simply be 2, would that be L? This is 1 nanometer down here. So we have root 2. I'm imagining that 1 nanometer. Root 2. So it's 1 nanometer. Okay, so we'll have root 2 sine pi x, because n is 1. Then, so I mean, we're just thinking of it in terms of nanometer, right? Phi 2 of x will be root 2 sine 2 pi x. And then phi 3 of x is root 2 sine 3 pi x. These are the corresponding eigenfunctions. So key takeaway, the eigenvalues of the Hamiltonian operator represent the possible energy level of the quantum system, which are quantized. And then the eigenfunctions correspond to the stationary states of the system. Then in a one-dimensional box of 1 nanometer, an electron's lowest energy. Okay, I guess I want to write this. I think it's important to write this. Key takeaways. Key takeaway. Of course, I'm still going to show the Python code. In fact, okay, let me talk about the takeaway before I talk about the Python code. So I don't know. Okay, let me go for the Python code, sorry. Yes, let's go for the Python code. Okay. Yeah, this is what this looks like. So we are talking about quantum application of eigenfunctions there. So we have all the necessary things defined, the box length in meters, 1 nanometer, the h bar, that's the reduced Planck's constant, and we have the mass of an electron, which is 9.11 times e raised to minus 31. Then we have the energy levels, 1, 2, 3. So you can place as many as you want, as many as levels you want to think about. So we have the value of x now, defining from 0 to the full length, right? In 1000 divisions for easy visualization. Then we define the wave function. So this is the formula here, the whole square root of 2 over ln pi sine blah blah blah, all of that. And then the energy levels also defined according to the formula. Then so once you just visualize this, I just run this, and then you have the beautiful graph jumping out. So you have the wave functions of a particle in a one-dimensional box.